I know our next guest or speaker as Senator Zwicker, one of the most thoughtful and nicest legislators, down in Trenton. But he also has a separate role. Senator Zwicker is a lifelong New Jersey resident, but he's also the head of communications and public outreach at Princeton University's Plasma Physics Laboratory, a world leader in developing an advanced form of energy known as fusion. I could go on and on, but we're obviously still short of time. So, we've been talking about fusion, I think, for quite some time. The senator has been talking about it for much longer than I even knew it existed. He's here today, not with the senator hat on, but he's here to talk about fusion as a scientist. So, Senator, welcome.
Thank you, Ray. Thanks, everybody. If you've heard me speak before, you've certainly heard me make a reference to fusion. My typical joke is that I'm not going to talk about the economy or taxes or housing or whatever, but it's going to be a 2-hour lecture on fusion. So today I'm proud to announce that we have a 2-hour lecture on fusion. I know it only says 30 minutes, but I have 150 slides, and we're going to go into a lot of technical detail. So, the path to fusion energy, is it the future, right? Of course, I'm going to say the answer is yes. The joke is that fusion is the energy source of the future, right? Energy source of the future always has been, always will be. And I'm here over the next 30 minutes to hopefully convince you that we're in a really new place when it comes to the development of fusion energy here in New Jersey and around the world. But first, I should make sure you know that it turns out that fusion has already been perfected, right? And I don't mean by the sun, which is the closest fusion reactor to us right now. That's 93 million miles away. But I mean, fusion was perfected in 1985. And if you don't believe me, I have photographic proof there. So it was in the documentary Back to the Future, where Mr. Fusion was powering up the car at the end of the movie. So if you don't believe me from that, we can go to 2004, and there's fusion in Spider-Man 2. So the good news, you can see it there, is they actually managed to put a picture of the sun into that one. If you still don't believe me, well, there's clearly fusion in 2008. That's Iron Man, the first Iron Man movie. Interesting thing about that one is that behind them in blue, that actually is a picture of a fusion reactor. I don't remember if that's the one from Princeton or there's another machine out in California, but the producers actually decided to get something that was close. And we can go to 2012, so it gets a little bit smaller and is possibly going to blow up and be turned into a bomb, and Batman is fortunately going to fly it out over the sea, and Catwoman's going to help him. Any questions? Thanks for the lecture. Appreciate it. We're done. And that is a real photograph in Plainsboro, New Jersey. I was just there earlier this morning. That's the National Spherical Torus Experiment upgrade at the Princeton Plasma Physics Laboratory. And that's what I'm going to spend my time talking about, is now the reality of fusion. To put some perspective on it, there's a person right there to give some idea. It's approximately 3 stories tall, which makes it in the world of fusion reactors a pretty small machine. But this is a machine that took me 20 minutes to drive here and is right next to us. Would be delighted if anyone's interested in a tour. Always happy to give a tour. So now let's talk for real about fusion, its prospects, what it is. So fusion is, and the reason why I have drunk the Kool-Aid is it is genuinely the ultimate source of clean electricity. And you can see the quote from Stephen Hawking, the cosmologist behind me, when asked in 2010, what problem do you hope scientists have solved? I would like to see nuclear fusion become a practical power source, providing an inexhaustible supply of energy without pollution or global warming. And so that's what this is about. It is one of the greatest scientific and engineering challenges ever attempted by human beings, is to turn the power of the sun, I should have said that with a Spider-Man, right? The power of the sun in the palm of my hand. a little bit bigger, right? But it's about, can we turn fusion into a practical source of energy? So of course, I mean, this is a perfect crowd to know, you already know this, that energy consumption is going up. You know, why do we need fusion? Why are we talking about nuclear? Why are we talking about battery storage? Why are we talking about wind and solar? Right? Energy consumption is going up, and this data is from pre-pandemic, but energy is basically going up regardless. That's the pandemic I look at as just a blip. But this is good. Right? We want energy consumption to go up because it correlates with increased standards of living. And so this is quantity of electricity that's here, and this is the Human Development Index. And so there we are with Canada. But as energy goes up, with that comes clean water and heat and air conditioning depending upon climate, access to a variety of different things, including good high quality medical care. So we want energy to go up. So where do we get our energy from? So a couple things to point out here, right? So look at, this is global, and everything's sort of going on, kind of trickling up until the 1940s into the 1950s, when total energy goes up dramatically, right? And so we get that, there's the biofuels, coal, oil, natural gas, hydroelectric, and nuclear. And solar and wind are a sliver. They're just a tiny little sliver of the worldwide energy production right now. And so in all of our discussions, we talk about here in New Jersey, let's increase offshore wind. Let's make sure we keep our solar industry going. How do we keep our nuclear fleet alive? What does next generation nuclear look like? But this is where the global energy consumption comes from. So what I'd like to do, so I pointed out in 1940, that's when we see the big increase. Can I say this to the person who has the computer, that's an animation, can you click? So before you click it, stop for 1 second. Right? So what we see here is the world. Let me just explain what you're about to see. Blue is, this is the average global temperature. Blue is cold, red is hot. And it's averaged over these periods, these 5-year periods of time. So this is back in the 1890s. So if you look at both the color that's there, and then as the years change, it'll go up to 2021. So can you go ahead and play that? So you can see it. It's blue with little yellows that are around there, but nothing really is happening. That's the 1930s, 1940s, 50s, into the 60s, 70s, 80s, and you can see what starts to happen, 90s, 2000s, 2010, all right? That's just data. That's not projections. That's just data. Look at the Earth, right? And we talk a lot about our common experiences. We talk a lot about the fact that people understand weather, right? We all check, what's the weather today? Is it gonna rain? Is it gonna be warm? Do I wear a jacket? But this is climate, and this is on average, right? So the Earth is warming, and it's up to us to decide what to do about it when it comes to, are we going to adapt, and what we're doing when it comes to energy production. And that's what fusion is about. Because if you imagine, oops, what if there was an energy source that had all of these, right? Safe, carbon-free, sustainable, inexhaustible, right? There are, as you'll see as I go through the slides, hundreds of thousands of years of fuel on the planet for fusion, right? We will probably go extinct as a species before we run out of fuel. Provides baseload energy. What by that I mean firm, meaning fusion doesn't care if the sun is going to shine or if the wind is going to blow. Fusion will just be baseload, constant energy. No geological storage. It doesn't need large landmass, whether that's for turbines or for solar panels. Imagine just a regular power plant right now, 1,000 megawatts, whether it's nuclear or fossil fuels. And the idea is we will one day, if we can perfect the technology, start to build right next to them fusion reactors, fusion power plants, and we'll just right on those sites, and perhaps in South Jersey one day down by the nuclear plants, move the connectivity to the grid over and have fusion electrons on the grid, right? And energy security. We're talking about, this is a worldwide project. The whole world is working on this, but the fuel is here. We don't have to import it at all. So it provides energy security at the same time. It is the ultimate energy source. So that's it. It's all about making the machine that can create a star in a machine here on Earth and turn it into practical, affordable electricity. That's the goal. So something that people don't realize is that the entire worldwide effort for fusion started here in New Jersey. It started with Professor Lyman Spitzer, a renowned plasma physicist at Princeton University, who was asked by the United States government back in the 1950s to explore the peaceful use of fusion, which is understood theoretically, for making energy. Professor Spitzer, who I never had a chance to meet, remarkable, remarkable person. He's also the first scientist to propose putting a telescope into space to avoid atmospheric disturbances, which became the Hubble Space Telescope. And there's now the Spitzer Telescope named after him. So and he's standing next to one of the first fusion devices ever built on the planet. You can see it's being held together by 2x4s and pieces of wood, right? So we've come a long way, but we're not quite done. Another thing is people don't realize that the United States' national laboratory, Department of Energy National Laboratory for the Development of Fusion Energy, is here in New Jersey. Ray mentioned it in his kind introduction of me. The Princeton Plasma Physics Laboratory is the country's national laboratory. There's about 650 of us that are there. We are part of Princeton University, but we're also a national laboratory. And so when you don't see me in either the State House or my legislative office, I'm sitting right there. And the machine that I showed before, and I'll show you again, is over in this building right here, right? And this is right off of Route 1. So we were too big. At first we were too top secret in the first couple of years. So Professor Spitzer put this facility in farmland. And now we're just too big to fit onto the main campus. Nothing we do is classified. Everything is available and open. We're just developing the technology. Okay, so we're the Princeton Plasma Physics Laboratory. So I'm gonna have to spend just a few minutes talking about just what is a plasma. I promise in the rest of my talk, there is only one equation, and I guarantee you, every single one of you know this equation and have it totally cold. So first of all, what's a plasma? So plasma is commonly known as the fourth state of matter: solid, liquid, gas, plasma, right? Solid, think of an ice cube. Add energy to it. What happens? It heats up, it warms up, but it changes its state from solid to liquid. Take that water and add more energy, it changes its state from liquid to gas. Heat up any gas. It could be water vapor, it could be any gas. And what happens is the electrons, which normally go around the nucleus, which is protons and neutrons, right? The electrons now have so much energy that they can just be free. And so the difference between a gas and a plasma is the free electrons. That's it. But the sun is a plasma, lightning is a plasma, all the stars are a plasma, 99% of the visible universe when we look out in the night sky is plasma. Which means that everything we know about the universe, everything we know, expansion of the universe, star formation, is by measuring the light that reaches us from plasmas, right? We still don't know what dark energy and dark matter is. We're working at it. The problem is we can't observe it because it's dark, but we'll get there. But it's all about understanding plasmas. Northern Lights, one of the things on my bucket list that I have yet to get to is to go see the Northern Lights, all plasmas. Neon lights, fluorescent lights, plasma TVs, and the hottest part of a flame. All of that is plasma. Okay, so for fusion, the easiest way to explain what fusion is to explain first what it's not. It's not fission, in the sense that fission is taking a large atom like uranium and splitting it, and that gives off excess energy. Fusion is the opposite. Let's take a small atom like hydrogen and combine it, make helium, but that also gives off energy, right? The issue with fission is that you can have a chain reaction, that the neutrons that are in white can start their own fusion reactions. And so a fission power plant is designed to control that, to moderate that, right? And that's why we get worried when something happens, whether it's an earthquake or a war or a tsunami, right? A fission power plant is just designed to make sure a chain reaction doesn't happen. Fusion is also the opposite in that it doesn't happen on Earth naturally, which means we have to force it. And that's where the technology comes in, and that's where the difficulty comes in. So the fuel from fusion is there, right? The Earth is 2/3 covered in water. We're talking about combining hydrogen into helium, fusing it together and giving off energy. So that's why we say practically inexhaustible. Because if you take the top inch of Lake Erie, top inch, it's a big lake, and you were to hypothetically pull out the fusion fuel out of that top inch, it is equivalent to nearly all the oil left on the planet. Right? That's why we want to do this, because that is one big lake, but we're not even talking about the oceans. It's naturally right in seawater. And those leading candidates are, we call them isotopes of hydrogen, but these are just hydrogen atoms. So tritium and deuterium both have a single proton represented by the blue sphere with a plus sign on it. That makes them hydrogen isotopes. And what happens, the reason why we choose these is because you get more energy out for every fusion reaction. But deuterium exists naturally in seawater, easy to take it out. And tritium, while it doesn't occur naturally in seawater, we have a scheme where we'll just breed our own tritium while we're doing our fusion reactions, once we have this up and running. So that's why we say practically inexhaustible. No carbon, helium, who cares? Blow up a bunch of party balloons, we're good to go. That's what we got to do. So, all right, here's the one equation. So where does the energy come from? So the weird thing is that if you take a deuterium and a tritium and you fuse it together and you get out a helium and a neutron, all you did was rearrange where the protons and the neutrons were. So it would be like all of us saying, let's just have a giant scale underneath us, get some, whatever this whole room weighs, and then we go sit somewhere else, and now we get a different amount for what we weigh, which doesn't make much sense. But when you rearrange them, you get a lot of energy coming out. And the equation that is tied from energy to mass is? I hear some people say it. All right, let's make sure you're awake. E equals mc squared. So Einstein helped us figure this out 100 years ago, right? So the fact that we rearrange what are called nucleons from hydrogen into helium means we get energy out. That change in mass that's here gets turned into energy, and a lot of energy. So we fuse, we make energy, we just need to turn it into electricity. Fusion is the energy source of all the stars, and right here in the sun is hydrogen, the core of this, all of our stars, all the neural stars. It's just hydrogen fusing together, protons that are combining, right? So it's creating a star on Earth. So now it is, how do we make a container to hold on to a star? So this is a 30-second video footage from a NASA satellite of the sun. And what you're going to see is the edge of the sun burp, if you will, and spew out plasma. So take a look at this. Way. So a couple of things I want to show. First of all, look at the size of the Earth. That's us compared to the sun, right? So the sun is obviously so much bigger than the Earth. You can put 1 million Earths inside the sun if the sun was a giant ball and the Earth was a marble. And then the other thing I wanted you to see was the fact that the plasma that the sun is spewing out is returning in this rain in a very specific way. And what it's doing is it's following the magnetic fields of the sun. And that's our big clue. The sun has natural magnetic fields. And plasma loves to follow along magnetic fields. And that's what's happening there. So the clue is, okay, great. We're not going to make something that big, but if we're going to make a miniature star, and we know that plasma follows magnetic field lines, then let's make a container that has powerful magnets and make them, instead of flowing this way, just go into a circle, and then we'll heat it up and we'll make fusion. That's what these machines are doing. They look like this. This is just a cartoon. The idea, imagine a donut. You can make it a Krispy Kreme donut, I don't care. Any donut you want. The cream in the middle is the plasma. And the brown bars around, so that's the red is the plasma. The silver represents a vacuum vessel. So we're just going to recreate conditions of outer space and put our hydrogen gas in there. And then the brown represents powerful magnetic fields that are on the outside. That's a cartoon of what we have to do. Back to Plainsboro and Princeton, that's what it looks like. So the container is, I don't know if my cursor is working, the container is in the middle. The red bars, there we go, right there, those are the powerful magnets on the outside. And then the plasma goes around and around, and everything else you see here is just to heat the plasma up. We can heat that plasma up from room temperature gas to 100 million degrees Celsius, which is much hotter than the core of the sun, in about a second. Room temperature to 100 million degrees in about a second with all the equipment that is here. We are a PSE&G customer. I know they were here before. We're one of their best customers. I also asked, do we have a payment plan? Like, do we get a monthly payment plan? So what do? We actually slowly, when we're running this experiment, we slowly pull electricity energy off of the grid, and we store it in underground massive flywheels, because when we're ready to turn this on, we don't want to cause a brownout on campus. So we can just pull that energy off of the flywheels, right? But everything else you see here is related to either heating up this plasma like that, holding onto that plasma with the magnets, or this is an experiment, so we're trying to perfect the technology, a lot of instrumentation to figure out what's just going on. That's inside it. So a couple of people working on the inside of it to the left. You can see the rectangles are made out of graphite. It's sort of like what was on the bottom of the space shuttle when we were flying the space shuttle. So it's to protect the stainless steel vacuum vessel with these graphite tiles from the plasma that may leak out. And that's an actual image of the plasma. And you can see, again, it's following part of the magnetic field. There is plasma out over here, but it's so hot that it's not emitting visible light. It's emitting X-rays. If we had an X-ray camera, then you would see bright spots more in the middle. And in fact, around the world, magnetic fusion devices are all some form of donut for the most part. And so the largest machine in the world right now is in the UK. That's the Joint European Torus. The Germans have something that makes the magnetic field a little bit different, but is still a magnetic bottle. You can see their magnetic coils are kind of funny shaped, just a different way to try to get to that magnetic bottle. And then finally, the entire world, the entire developed world is building a machine you may have heard of right now. It's under construction in the south of France called ITER. This will be the first machine, perhaps, that we will ignite the star. All of our experiments so far, if you think about a fireplace and you're getting a fireplace started, what do? You put in your fuel, you have your match, you light up the kindling. Once it's hot enough, you blow out your match. ITER, or perhaps one of its competitors, I'll show you in a second, will be the first machine to blow out the match. And at that point, it's self-contained, it's running itself. Then we start figuring out how to perfect it and how to turn it into electricity. That'll happen over the next 10 years. So we got to create electricity. So here's a quick cartoon, a couple more equations that I forgot about. But the bottom line is this. We are going to make heat to make steam to turn the blades of a turbine. No different than how we're making electricity right now. right? In the end, this is probably the most complicated way to take water, heat it up, make fusion reactions, to take other water, to heat it up, to make steam, to turn the blades of a turbine. But once we do it, it never stops. So the big question, of course, is when, right? So the answer is now, without a joke, sooner than you might imagine. Because what's happening right now is a worldwide acceleration towards fusion driven by the private sector. For the longest time, fusion was just a government project. No investor would ever want to invest in it. And 10, 15, 20 years ago, things started to change. Philanthropic investors, someone in the equivalent, say Bill Gates, right? Who has enough money to say, I don't care if there's a return on investment, I'm willing to try to accelerate it. That started, but in the last few years, billions upon billions of private dollars have gone into fusion, to the point that we now have the National Academies of the United States calling it's time to accelerate fusion and get fusion electricity on the grid by 2035 to 2040. Congress proposing a variety of different public-private partnerships. Congress has put $50 million into a bill last month to start to accelerate public-private partnerships where we will pay out of the federal government the public part of it. Commonwealth Fusion Systems out of MIT has raised almost $2 billion in Cambridge, Massachusetts over the last few years. TAE Technologies out of California, about $1 billion. Princeton is working with 5 to 7, including startups, including we now have 2 startups here in New Jersey that are just getting off the ground, but are going to go in the next couple of years from paper studies into building devices. And so it's really a question now, it's no longer a question of if, it's when and how soon, right? So we continue to work on innovation, both within government laboratories and with the private sector. But I am feeling relatively confident now that we will see fusion in all of our lifetimes and that it will be the game changer it's always supposed to be. So I have one more thing that I want to end on, which is a video coming up. But here's what I need you to do. The video is much too long. Can you fast forward it to exactly 6 minutes? And I'm just going to show the last minute. So as they're doing that, before you hit play, so, you know, I'm a scientist, I'm a politician, I'm also a cartoon character, as you'll see in a second. Most people tell you you're a politician, you've been a cartoon character for a long time. But a colleague of mine named Arturo Dominguez and myself a few years ago were filmed talking about fusion, and then a very talented animator put it together into something. It's on YouTube, and it's gotten hundreds of thousands of views. So are you at precisely 6 minutes? You are. So you'll recognize my voice, but I'm in the red hoodie. Go ahead.
So all the machines you saw today, you know, before you talked to us, were just different ways to make a magnetic bottle. And there's other people you can read about that use electric fields, they use lasers, or whatever it might be. But in the end, because we can't use gravity to cause fusion, we got to do it some other way. Because there's 2 questions, right? There is can we build the machines that can do this, right? That's the first question. And we say yes, and we can debate that scientifically, and we can debate the engineering and the technology and all those sort of things, right? But that's not enough to make usable electricity. You also have to have everything else in place so that the energy that you create has to be competitive economically with the fossil fuels, or with fission, or with solar, or with wind. I mean, if we get there, and we will get there, it's a game changer. That part's, you know, not the hype. So why don't we have it, and how long is it going to take? I would say currently the answer is never, unless we are really serious about funding this. If we're wrong and we can't do it, then the planet goes on to whatever it does, right? If we're right, it changes the planet as we know it, because it's a completely new paradigm in a source of energy. Right? So the question becomes, are we willing to take the risk to find out if we're right? I mean, don't you want to be a part of something that changes the planet? That's the bottom line.
bottom line. Don't you want to be a part of something that changes the planet? So that's what I've got. We got a couple minutes left for questions. But I think, in my mind, I start thinking now about where is that first fusion reactor going to be, and why shouldn't it be in New Jersey? But let me stop there. Happy to answer any questions, and thank you so much.
Any questions from the audience? We have a microphone.
Sure.
No, we have a mic coming.
Thank you, Senator. Thank you, Senator. That's one of the best, I'll just talk loudly, one of the best presentations I've seen in a long time. Question is, if you start the reaction, can you stop it?
Yeah. So if you couldn't hear it, the question was, once you start the reaction, can you stop it? And unlike fission, anything that goes wrong will stop it, right? So Mother Nature does not want fusion to occur on Earth easily. And so if the magnetic container, for instance, were to spring a leak, the reaction just stops, right? There's no runaway possibilities of any kind. Because remember, we have to force it to happen by heating up this gas into that plasma state to a temperature 7 to 8 times hotter than the core of the sun. If anything goes wrong, it cools down in a millionth of a second, and the reaction just stops. So there's no health hazards. There's no safety hazards. That's the big reason why we push so much for this.
Anyone else?
Sorry. Yeah, this is for the scientist and the senator. Question is, what are the technology challenges or technical challenges as a scientist that are still remaining to overcome?
Yeah,
Can you
so
say a little more
sure.
about that?
So why don't we have it right now? What are the technical challenges, right? There's a couple of them. So the magnetic container is not perfect. And in fact, we design it to leak on purpose, but you want to control that leak, which means that you've got 100 million degree plasma in the core, and maybe 10 meters away or less, you have a room temperature solid stainless steel wall. So one of our great challenges is that first wall material. It's an engineering challenge, right? And making sure we have that just right. Because if the plasma leaks out, and it will, and it causes any of the wall material just at an atomic level to come back into the plasma, it can cool it down. That's one. The other one is when you heat up these atoms to these temperatures, they're moving quickly. And there are these strong magnetic fields, there are electric fields, they're all going around. And what happens when they're going around like that, and you want them to just collide, is there's also, I'll call it turbulence. It's a turbulence, the same sort of turbulence that we'd experience when we're in an airplane. And what that turbulence does, normally we experience it as just shaking the airplane. But that shaking causes plasma to leak out at a higher rate than we want. And so controlling that is another key thing here. So those are probably the two biggest challenges we have, right? And then the rest of it, I'd say there's one more. It is an engineering challenge, but it's an economic challenge, because I'm confident we can solve those. What we have to prove, like any technology, is that we will be economically competitive. I said that quickly in the animation. Because if we make fusion electricity and it's 10 times more expensive than whatever, then the market won't care, right? And I think that's the other piece of this. Like any new technology, the cost of electricity will be high, and how do we make sure we're driving that down?
We have time for one more question. I'll throw one out then. So let's assume you're correct, and by the way, you said it's going to be in our lifetime. Some of us are older than others, just to put that out there.
I'm an optimist, Ray. I'm only an optimist.
2035, electricity into the grid. Once that it's no longer a prototype, once that marketable reactor is in being, how quickly can it scale up?
Right. And that's a function of, discussions you've had here of how quickly can you build, let's say, a small modular reactor? How quickly can you build any power plant of any kind, right? That gets interesting because right now, if you follow the headlines down in DC, you know that part of the deal for the Inflation Reduction Act was a piece to start to reduce the time for some of the regulatory processes. We're going to need that as well because, sure, we're talking about if we got the go today, we're probably 10 years out from building something, if not more, right? And so we're going to have to figure that part out. But I would say that's true not just for fusion, that's true for next-gen fission, that's true across the board.
Clean. Thank you.
Thank you, everybody. Appreciate it.